A proper index can make your query 10, 100, or even 1,000 times faster. Sounds amazing, right? But nothing in life comes for free. Every index has a cost. It slows down writes, consumes memory, and even makes recovery after a crash longer. In this video, we'll look at the real price of an index, what really happens during inserts, updates, and deletes, and how indexes affect logging, backups, and ongoing maintenance. For DML, I skip PostgreSQL for now. It has a very specific implementation of MVCC, multi-version concurrency control, so I'll make a dedicated video about that soon. Hi, I am Jakub from DBBoost Academy. As I showed in the previous video, an index is actually a copy of our data. Its main job is to make searching and sorting much faster. So without further talking, let's get to work. Let me introduce my sample table. It contains movies. The columns are ID, the primary key, movie name, country, score as voted by people from 0 for the worst movie to 100 for the best one, language, and a few others. Since ID is the primary key, there has to be an index for it. So I have a table of movies and one index, the one that supports the primary key constraint. As we already discussed in the first video, an index, just like a table, is stored in 8 kilobyte pages. Whenever we change our data in the table, we also need to keep the index up to date. Let's start with inserts. When we insert a new row into a table, all we need is a page with enough free space. A single row can of course span multiple pages if it's large, but let's keep our example simple and assume it fits into one single page. Now we also have to update the index, our copy of the data. But with an index, we can't just put the new entry anywhere. The index must stay sorted. So the database first traverses the tree, finds the correct position, and only then inserts the new index entry there. Because of that, inserting with an index requires extra I/O for the traversal. And notice what happens in this example. One new row, represented by the green color, results in 2 page changes. One in the table and one in the index. So instead of writing just 8 kilobytes for the table page, we also write under 8 kilobytes for the index page. That's 16 kilobytes total, basically double the work. Of course, it's also common to have more than one index on a table. In that case, every time you insert a new row, the database has to add it to each index as well. That means traversing every index tree, finding the right place, and inserting the new entry there. So each additional index makes inserts slower and requires more work from the database. Let's check deletes. A delete is tricky because we want to remove a specific piece of data. For example, suppose I want to delete all movies with the name Shockwave. To do that, the database first has to search for the rows to delete. In my case, I don't have an index on the movie name, so I have to scan the whole table and fetch all the pages with rows where the name equals Shockwave. If I had an index on the name, I could use it and avoid this expensive search. So after the full table scan, I finally get to the table page and delete the row there. Now it's time to update the index, of course. The row I just read gives me all the information I need to traverse the index and delete the corresponding entry again. I changed 2 pages, one for table and one for the index. But unlike inserts, a delete first needs to find the rows that match the where condition in the statement. That makes deletes good candidates for index tuning, because a missing index can make them extremely slow. Still, consider how often deletes happen, or whether other queries, DML or even selects, could benefit from the potential index too. Because as you can see, there is always a price. Deletes and inserts affect all indexes on the table. There are a few exceptions, like filtered indexes or other special cases depending on the database engine, like Oracle and null index keys. I'll mention filtered indexes later in this series. The last DML operation is an update. With an update, you usually use some conditions. It means you need to search the table pages first, just like with a delete. But unlike a delete, the index needs to be modified only if you change a column that's part of the index. Because of this, I added one more index for language and score. So I have two indexes now. Let's say I want to update the score for the movie with ID 8285 because someone new just voted. First, I need to find and read the page with the row for ID 8285. Since I have an index on the ID, it's an easy task, just traversing the tree. Second, read the table page and update the row. And third, update indexes properly. I have two indexes. I don't have to change the index for ID because ID stays the same. However, I need to change the index for language and score because score was updated. I need to find the index entry for my row. That's this step. I can't simply overwrite the value because the index has to stay ordered. To keep index ordered, I have to first remove the old index entry. Second, add the new entry with the new value in the proper place inside the index. So do another traversal. So, index update is actually delete and insert. In my case, I updated two different pages in my index. It can happen that the new entry fits into the same page. Everything depends on the values. The key is to keep index ordered. Let's make a quick recap. Every DML operation touches both the table and its indexes, but not always in the same way. Inserts can go to any table page with enough free space, but each new row must also be added to all indexes on the table. Deletes first find rows that match the filters, and then remove their entries from all indexes as well. Updates also locate rows based on filters, but modify only those indexes where one of the index columns has changed. In short, inserts and deletes affect all indexes, with a few exceptions, while updates depend on which columns were modified. But this is not the only cost. In relational databases, to protect our data and ensure the durability, we use a transaction log, sometimes called a redo log. This log is a complete history of all changes and data modifications, including those caused by indexes. Let's use our update example again. We modified the table page, and this change must be logged, but we also modified two pages of the index. Those two changes must be logged too. So modifying indexes represents additional changes we need to cover by the log, meaning the log gets significantly bigger. This leads to higher IO write load, and more data has to be written sequentially and quickly to the disk, increasing the burden on your storage system. Another cost is longer recovery time. The backups will be bigger too, as the physical footprint on the storage is increased by the indexes. More log records and larger files mean that the entire process of database recovery takes longer. You could technically restore only the tables and recreate the indexes later using DDL scripts. However, this is rare in production, as the time needed for index creation would severely violate your RTOs, recovery time objectives, and SLAs, service level agreements. Now let's talk about the ongoing maintenance cost of these indexes. Maintenance includes generating statistics that the query optimizer uses to decide whether to use an index or not. This may sound like a minor thing, but in 24/7 systems, the maintenance windows are often extremely small, and these tasks consume valuable CPU and I/O time. Another heavily debated topic is rebuilding indexes. It's very database engine specific, first of all, and there are some DBAs love rebuilding, some don't. The rebuild debate is similar to the discussions surrounding other performance topics. You can find a lot of strong dogmatic statements. For example, you should rebuild when fragmentation is above XYZ%. However, the reality is that such fixed rules are misleading. You should understand the specific internals of how your database engine handles fragmentation and decide if the rebuild makes sense. Why? Because rebuilding an index can cause more harm than good if it's used inappropriately. If you don't need it, it simply wastes your maintenance window. The last point, which we already touched, is the storage and memory consumption. Indexes are copies of our data. So they increase the physical storage footprint of your database and they consume memory from cache. So as you can see, indexes are a trade-off. They make some actions faster, but every single index slows down writes and adds overhead for maintenance. You should not blindly add indexes for every ad hoc or rarely used query. I always tell people that it's easier to add a new index than safely remove one. Understanding this real cost is the crucial first step toward effective database performance tuning. That's it for today. I hope this deep dive into index costs was helpful. If you have any thoughts or ideas for future videos, let me know in the comments below. I will read all of your feedback. And if you found this video useful, feel free to hit like or even subscribe. Thank you for watching. I am Jakub from DB Booster Academy, and I look forward to seeing you next time. Take care.